Let's keep going. Example number 2. Determine the equation of the line tangent of or to y equal to e to the x, where x equals to 1. So again, if you look at this carefully, we've done this type of example many times. The only difference is the function, which is e to the x, versus other cases. So again, the first step is you want to find this general derivative. So y prime is going to be e to the x. And again, for x equal to 1, the slope, which equals to y prime of 1, equals to e to the power of 1, or simply e. So this means the slope is going to be e. Now to find the equation, you need to find the coordinates. So the fact that x equals to 1, you have to go back and figure out the corresponding y value. So you can plug in x to be 1, which means y is going to be e. So this tells you that the coordinate x, y is going to be 1 and e. And again, we can put a box around that. And the fact that you have both the slope and the point, the rest, you've done this many times. So y equals to mx plus b, e equals to e times 1 plus b, b becomes 0, which means y equals to e times x. Or if you put this in standard form, you're going to bring everything to one side, set this to 0, so e to the x minus y equals 0, just like that, or like that. Example number 3. Again, this is from your textbook on page 233, number 12. Again, you can press pause, you can try this first, and when you press play, I'll be right here and we'll take it up step by step. Here we go, number 12. The number n of bacteria in a culture at time t in hours is n of t, which equals to 1,000 times, in brackets, 30 plus e to the power of negative t over 30, close bracket. Part A, what is the initial number of bacteria in the culture? So again, you have to know how to translate this from words into math. Initial means at the beginning. So this tells you what happens when time is 0. Initial, when time is 0. So I'll write this on the side for you. So for part A, this means you're looking for n of 0. And of course, if you plug it back in, this will give you 1,000 times 30 plus e to the power of negative 0 divided by 30. And of course, you can take the calculator, you can do a little bit of mental math, but this term, e to the power of 0, that's going to equal to 1. And if you work it out, this is going to be 31,000 bacteria when time is 0. Part B, determine the rate of change in the number of bacteria at time t. And again, this is how you translate from words into math. Rate of change, that means you're finding the derivative. And in this context, the derivative is going to be n of t. And that's what they're asking here. So again, if you look at part B, to find the derivative, n of t, this equals to, again, if you want, you can expand this first and find the derivative. So maybe I'll take a step back. Let's go back to n of t first. If you put this in expanded form, this would be 30,000 plus 1,000 times e to the power of negative t over 30. So again, all we're doing is we're expanding this. Now we're ready to find n prime of t. And in this case, this is going to be 0 plus 1,000 times e to the power of negative t over 30. Don't forget to multiply by the derivative, which is negative 1 over 30. So the final answer is going to be negative 100 divided by 3 times e to the power of t over 30, just like that. And again, that's the rate of change. Part C. How fast is the number of bacteria changing when time equals to 20? So again, you got to be careful here. When you translate the word fast, again, that means rate of change, which is the derivative, specifically at time equal to 20. So this in English just means, or in math, just means what is n prime of 20. That's what you're trying to calculate here. So if I keep going underneath here, part C, n prime of 20, that's going to be negative 100 divided by 3 times e to the power of 20 over 30. Again, you can take your calculator, you can work it out, and if we don't match, you can make a comment below and I will follow up accordingly. But it should be negative 17.1. Don't forget the units. It would be negative 17.1 bacteria per hour. Part D. Determine the largest number of bacteria in the culture joining the interval when time is in between 0 and 50. So again, you got to be careful here because if they give you a domain, and again, time cannot be negative, so it makes sense that time is in between 0 and in this case 50. You got to compare a couple points. So number one, you got to find critical points. Number two, you compare the critical points with the endpoints, and out of those points, the largest number is the maximum. So again, largest number implies what is the maximum. And this is how you do it. Now, in part D, first, let's find the critical point. So we set the derivative to be 0. This means 0 equals to negative 100 divided by 3 times e to the power of t over 30. And by inspection, you can tell this is not possible. And again, it's perfectly okay that you cannot find a critical point or that there is no critical point. It's not okay that you can't find it, but it's okay that there is no critical point. And that just means when comparing, you're simply looking at the endpoints. So again, since time is between 0 and 50, you're comparing what happens when time is 0 to what happens when time is 50. Again, you can plug it back in. You can take the calculator, but you can tell that n of 0, which is what we did, the initial amount is 31,000. And when you plug in 50, it's going to be approximately 301,889. Again, you can verify this by taking the calculator and you compare them. And by finding the largest number, that becomes the maximum. So in this case, the maximum is going to be, hold on, let's go back. I said 301,000, that's my mistake. It's 30,188.9. There was a decimal that I forgot to mention, that's my mistake. So again, if you compare them, the larger number is the initial population, which is 0,31,000. And again, this should not be a surprise because if you look at the function, it's e to the power of negative t over 30, and that negative implies there's going to be an exponential decay. One more part. Part E. What is happening to the number of bacteria in the culture as time passes? So really, as time passes, it's going to essentially hit some kind of limit. So it's really asking for end behavior. So if we take a look at the limit, as time is approaching to infinity of the function 1000 times 30 plus e to the power of negative t over 30, this will give you, and again I'll put this in quotation marks, in the world of limits, this is going to be 1000 times 30 plus e to the power of negative infinity over 30. And again, we're thinking about this in the world of limits. So this equals to, again, the 1000 remains unchanged. If you think about e to the power of negative infinity over 30, this will give you still negative infinity. And if you keep going, this equals to 1000 times 30 plus 1 over e to the power of infinity. And again, I hope you get the idea here. E to the power of infinity is basically infinity in the world of limits. 1 over infinity in the world of limits will approach to 0. So ultimately, this will give you 1,000 times 30, which will be 30,000 as your final answer. So what is happening to the number of bacteria in the culture as time passes is going to approach to 30,000 bacteria. Again, please take some time to try numbers 1 to 17 on page 232. And until next time, all the best, and I hope this makes sense.